Hello. So this is chapter 2 for the Top Hat textbook. With that, so we're going to be going through here. It's going to be talking about the functional groups, as well as quite a bit of naming of the organic molecules. So we're going to start off with looking at the various functional groups. So these are the parts of the molecule where the chemistry typically happens, so either right around that spot. But it also gives it the quite a few of the properties. So so the first one are the hydrocarbons. So these are if they're only have carbon-carbon single bonds, right? So that we call those alkanes. So they can be either in a straight chain or a cyclic in this form. We'll talk about that more later. If they can contain a carbon-carbon double bond, we call those an alkene. And if it's a triple carbon-carbon triple bond, it's an alkyne. So there's alkynes here, alkenes, and you can have a mix and match of them. So alkenes here, alkynes here, and this is one of the few times where it actually makes a bit of sense in the naming, in that the originally, so that if you look here at the suffix, say ane, and this was originally ine, but that would be way too easy, so they made it yne. So there's the vowels right there. There's also a benzene. We'll talk on some of that. And so this one is a very specific molecule. It is a hexagon. It's a 6 carbon ring. So 1, 2, 3, 4, 5, 6. Right, 1, 2, 3, 4, 5, 6, with alternating double and single bonds. So it has to have 3 bonds. Has to have be a 6-membered ring. Look at that. So this is a class of compounds called aromatics, and we'll talk about those in later chapters. What makes the benzene special is the fact that each one of these carbon atoms is sp2 hybrid, so each of them has a p orbital that's unhybridized, and so if you notice, they're all in alignment here, because remember, sp2 hybrid carbons are flat, and so with the p orbital sticking out, since they're all in alignment, what can happen is they can all smear out like this. And so if you sort of want to imagine this, so remember there's the top lobe and the bottom lobe. You can sort of see this as if you were to take, say, a hamburger, so hamburger patty or whatever it is, that would be the carbon groups, and then you would have donuts on like Krispy Kreme donuts or whatever it is on the top and the bottom. Those would be your buns. That would be what it would look like. So that, if you want to imagine it. So you can actually have, and we'll talk about this in a moment, you can have these things be coming off of here, and we'll talk about phenyl groups and benzyl groups in a minute when we go back to the, I should move these, later on. So the next class is the alkyl halides. So these are where you have the halogens. So if you come in here and you look at fluorine, chlorine, bromine, iodine, and technically acidine, these are the halides. So they're sometimes called halides, sometimes they're called halogens. You can sort of mix and match them, stuff like that. And so they are that class of elements, stuff like that, coming down in this row. So either one of these 4, consider this. Now we can designate those depending on what type of carbon they're hanging off of. So if here's the halide here, if you look at that carbon there, stuff like that, so how many other carbons are directly attached to it? Here it's just the 1, so we consider this to be a primary halide. For here's the halide there, so you look at that carbon, and so for here you've got 2 carbons directly attached, and for here, right, here's the halide, so you're looking at that carbon, and you've got 1, 2, 3 attached. And it doesn't matter how many, how long these chains are, how many carbons there are. So if you had something like this, so let's say you had a bromine, right, you would look at that carbon there. So you look at that carbon, and how many other carbons are directly attached to it? Well, there are 2. So this would be a secondary carbon. So even though that there's more carbons down here, you're looking at what's directly attached to it. So with this classification scheme, when you need to look, for this one and for carbons, right? So how many other carbons are attached? Well, in this case, it's 1, so this is primary. There's 2 directly attached, secondary. 3 directly attached, tertiary. 4 directly attached. And so for carbons, you can actually have a quaternary. You can have a quaternary carbon for that. But otherwise, you're looking at the carbon that the group is attached. So for alcohols, they are they are OH groups, something like that. But they are OH groups that are not directly attached to a benzene. So this actually has significantly different properties to it. So we call that a phenol, and so this whole group here would be a phenol. This would also be a phenol here. But if we want to look at alcohols, so that would be this OH is just directly attached to just a regular old carbon here. Stuff like that. So here you got a phenol, alcohol. This is an enol, but that's okay. You've got this mix of alcohols and phenols, with that, and so you have to be careful. So if it's just an OH, direct just to a regular old carbon, then it's an alcohol. If it's directly attached to a benzene, then it's a phenol. So this is a very special case. So alcohol classification is the same as the as halides, stuff like that. So again, you look at the carbon that it's attached to, and then how many other carbons are attached to it. And so this one is this one's a primary alcohol. So this is ethanol. So that's the one that's in your margarita. With it. So, but you can also have here geranol, which is in geraniums, right? So you look at that. You look at that carbon. How many carbons directly attached? Just 1. And even here, benzyl alcohol, you say, wait, hold on, that's on a benzene. Nope, there's a carbon between it. And so how many other carbons are attached? Just 1. And so these are all primary. So you look at that, how many are there? Isopropanol, so rubbing alcohol, right? So this is a secondary, right? So you look here, how many other carbons? 1, 2. Same thing here, menthol, right? So where that carbon is attached, right? There's 1 here, there's 1 here directly attached to it. So so this is a secondary. Tertiary alcohol, so you look at this one, I think this is a contraceptive, right? So you look at that carbon there where the OH is attached, right? And there's 1, 2, and 3. 3 carbons attached to that carbon directly, and so this is a tertiary alcohol. Now the reason why we're talking about these tertiary alcohols, tertiary halides, primary, whatever, is because they do actually have different reactivities. How they react is going to be different. It's going to be important down the road, and so we need to know whether or not the alcohol or the halide is a primary, secondary, tertiary to understand how they're going to be able to react. Next up are the ethers, and so these are the carbon cousins of an alcohol, something like that. And so instead of a carbon on one side and an OH, which would make it an alcohol or technically a phenol, you have an ether, which is an oxygen with carbons on either side. And so you'll see this here. So this R group, that just means any carbon group. And so it can be anything. They can be the same, they can be different, it doesn't matter. It's just there's carbon groups on either side. And so you can have it as part of a ring, you can have it straight chain, doesn't matter. Okay. Now, amines are the nitrogen equivalent of an alcohol. So instead of an OH, we have an NH. And remember, nitrogens typically like to have three bonds in a lone pair, and so they're going to have 3 things hanging off it. And it doesn't matter with the amine if there's hydrogens hanging off of there or not. And so you're just going to have a nitrogen with things hanging off of it. And so so here, right, you've got NH2. You could also have just carbon groups hanging off it. So this would be as an amine as well. So they don't have to have it does not have to have hydrogens hanging off of it. So this is an amine that's an amine as well. So they typically smell bad, stuff like that. And so this one here happens to be putrescine. There's also another compound that has a slightly different number of carbons in it. It's called cadaverine, because it smells like something putrefying meat, or a cadaver, or a rotten fish, or things like that. But they are incredibly important in biology. Some of that. So here it's amphetamines. They have this general this general structure. So methamphetamine has a CH group hanging off of here, and an alcohol, pseudoephedrine has an alcohol hanging off right there. Stuff like that. So, but they all have this sort of general structure to them. So, now this is amine classification. This one is this is the big exception. Normally it's going to be what is the carbon that the group is hanging off of, how many carbons are that one. Amines are the exception, because it's how many non-hydrogen groups are hanging off of the nitrogen, directly. Okay, and so here we have one non-hydrogen group, right? Yeah, there's three things hanging off of it. That's fine, but only one of them is not a hydrogen. So so we call that a primary. Here, a secondary, because we have two things that are not hydrogen. Here it's a tertiary, because there are three non-hydrogens. You can't have quaternary amines, so you could have this, but that nitrogen's going to have a positive charge. So this would be a quaternary amine. That is possible. We're not going to use it all that often, but it is possible with that. So again, amphetamines are primary, right? Because they only have, this one group hanging off of the nitrogen. Dopamine, again, so this is a primary. This is also a primary, right? Because it only has this one thing hanging off it. It's big, but it's only one thing. Here, nicotine, so that guy there, right? It's got three groups, three non-hydrogens, so this is a tertiary. Okay? And then this one, I guess technically you could call this to be a secondary. But this is a little more complicated because it's it's part of a benzene. So now the next few groups, they're all going to be based on this carbonyl group. So the carbonyl is the C double bond O. Whenever you see that, you're going to have to worry about what's on either side of it. Okay, and so for aldehydes, okay, so there's a carbon group on one side and a hydrogen on the other. For ketone, they're sort of cousins of each other. Here with ketones, it's a C double bond O with carbon groups on either side. So for this one, so formaldehyde, this is when you hear about preserving things, it's incredibly reactive. It's actually a dialdehyde, right? Because it's got hydrogens on either side. Acetaldehyde, this is what you give your hangover. Benzaldehyde, which is typically it uses a flavoring for cherry or almond, but even cinnamonaldehyde, stuff like that. So, right, so you've got a carbon on one side and a hydrogen on the other. Ketones, right, they have carbons on either side. So the simplest one is acetone, right? So because it's got carbons on either side. But methylethyl ketone, so again, just carbon groups on either side of that C double bond O, makes it a ketone. Carvone, right? So again, it's got carbons on either side of the C double bond O. So that makes it a ketone. Now carboxylic acid, okay, this one here, instead of having a hydrogen on one side, you have an OH on one side. So you have a carbon on one side, OH on the other. Okay, and so so acetic acid, so something like this, right? So acetic acid, this is the simplest carboxylic. This is a simple carboxylic acid, right? You got a carbon on one side and an OH on the other. Benzoic acid, right? Again, you've got C double bond O, you got OH on that side, carbon on the other side. So that's a carboxylic acid. Esters, this is a cousin. So just like the difference between alcohols and ethers, this one is the difference between carboxylic acid and esters. So for an ester, you need a carbon on one side, and instead of an OH, you have an O carbon. Like that. And so something like this, they're typically very sweet smelling. Something like that. And so, right, so you've got a carbon on one side, and then you got a carbon on one side, right? And an O carbon on this side. If it was an OH, it'd be a carboxylic acid, but it's an O carbon. Okay, so this is the big, so that's your ester group here. Okay, amides, these are the nitrogen versions of an ester. Okay, so you've got your C double bond O, and so you're going to have a carbon group on one side and a nitrogen on the other. So this is how you have to distinguish, so these are called amides. This is how you distinguish between an amine and an amide is for a nitrogen, does it have a C double bond O directly adjacent to it? If it does, then it's an amide. Otherwise, it's an amine. Like that. So just like acetamide, right here. So this is, right, you've got a nitrogen with a C double bond O directly adjacent to it, so that makes it an amide. And again, it doesn't matter that it's the other groups hanging off of the nitrogen. If there is a C double bond O directly adjacent to it, it's an amide. Okay. Now there is one other exception to the nitrogen, and this is the nitrile, and this is the only configuration going to have. It's a C triple bond N. So this is typically called a nitrile. You can also be called a cyano group because it's the basis of cyanide. With that, and so do be aware that sometimes it's just listed as CN, and the understanding is that is a C triple bond N. Right there. So you just have to know it about that. But even for something like this, remember that sometimes it's listed like that. We don't technically have to list the carbon there, but know that there is a carbon right here where that triple bond starts. So, okay, so this is the list. It's in the book. This is the list of groups that you need to know. There are a couple in here that we didn't talk about earlier. The sulfur version of an alcohol is called a thiol. So it's SH. So these typically smell really bad. So this is another one that smells like rotten eggs. The sulfur version of an ether, right? So it's called sulfide. Right, so benzene, ketone, aldehyde, carboxylic acid, acyl halide. So this one, this could also equal fluorine as well. Fluorine's fine. So this one is just a carbon on one side and a halide on the other. So remember the halides. Right? It's these fluorines. Sometimes it's listed as X. Fluorine. Well, let me get this in order. Chlorine, bromine, iodine. Okay, going down that table. So with that, and so you can have an acyl halide. So if you have a halide on one side, carbon on the other, or you can have an anhydride. And so for here, you've got a C double bond O, O, C double bond O. It's actually the way that they're made, at least traditionally, or at least originally, it was two carboxylic acids sort of pointed head to head. With that, and so you got a C double bond O, O, C double bond O. So this is another one that we didn't talk about, but you'll need to know. The reason for this is because we're going to be using these various functional groups for the rest of the course, and so I need you to be able to know those. So I don't have to keep spelling out what a ketone is, or an aldehyde, or an amide, things like that. And so you need to know what those are for. So please memorize those. Okay, so what you'll get is you'll get a molecule, and and what I want you to do is I want you to circle and name the groups. Okay, now I'm going to list this on here. You don't have to circle alkanes, cycloalkanes, which are these rings here, cyclic, pentagons, hexagons, things like that. You don't have to circle those, or benzenes, right? So remember, benzenes are 6-membered rings, so they're hexagons with alternating double and single bonds. Okay, you don't have to circle those. If you don't, by the end of this course, you don't know what a benzene is, you can't pick it out, then we have issues with that. So what you're going to do is just start at one end and go to the other. Now I tell you that there is if there is a non-carbon in something at a position, or if there's a double or triple bond, there's going to be a functional group there. Okay, so usually when it's, so this is Flovent, so this is for asthma. Now, in this particular case, I'm not going to do this on test, but just to let you know, if you're looking at these things, just as a reminder, the wedge, so this is showing you how things are oriented in space in 3 dimensions. So if you see a wedge like this, that means it's pointing out at you. If it's a dash, it's going away. So in this case, it'd be going into the iPad with that. So going away. But I'm not going to put that on there just so you don't confuse you. So usually you start at one end and go to the other. So I'm going to start here. So we have a C double bond O. And so what you do, right, you're going to be looking on either side of it. And notice how there's carbons on either side. So that means this guy is a ketone. Okay. Next up, do some other colors here. Here you've got a carbon-carbon double bond. Right? So that's an alkene, right? And there's also one here. So you've got alkenes there and there. So now you say, like, wait, hold on, it's a benzene, all right? Isn't that a benzene? Because it's a hexagon. It's got double bonds in it. No. This is what a benzene looks like. It's got to have the three double bonds in it, alternating. This one doesn't have it. It only has the two double bonds, so it can't be a benzene. Okay. Now these guys here, so this fluorine here, that fluorine there, so those are the halides. These are 2 halides. Right? You could also do halogens. Right? Hydrogens, don't have to worry about that. So for this one, right, we have an OH group, right, but it's attached just to a regular carbon. Now if it was a C double bond O here, right, just right there, then it would be a carboxylic acid. But we don't have that, and this is not a benzene. Okay, so that's not a phenol. So this is just a regular old alcohol. Okay. Now for this one, right, we have a C double bond to O, and it's O carbon, right, on one side and a carbon on the other. And so that one is an ester. Okay. Now this one here, this is one that's not on your list, but this one here is the sulfur version of an ester, and so this is actually a thioester. You don't have to worry about that one. And then the last one is you have that guy there, right? This one's a halide. Now, one of the things that happens is, so the atom can only be part of one functional group. So this is not an ester and then that be an ether. That's not how this works. It's a part of one big ester group. Okay, just like this sulfur is one big thioester, right? It's not a thioester and a sulfide. That's not what it is. It's just one big thioester group. This one is just a ketone group. So be careful. Okay. So on the exam, I give a point for circling it correctly and a point for naming it correctly. So if you don't know what it is, at least circle it. So I can give you a point. Okay, so next we're going to come into, now that we've sort of introduced the functional groups, now we're going to start in on naming. So the easiest one to start with would be the alkanes. Okay, we're going to be spending a lot of time on these just to give you sort of a lot of practice on naming molecules. Okay, so the alkanes, they only contain carbon-carbon bonds and carbon hydrogens. So these are the hydrocarbons, and they're mostly built by what's called cracking, something like that. And so what happens is they'll get the oil. They're usually from petroleum products. They get them out of the ground, and you put these and you heat them up to incredibly high temperatures, and and they start to break down. And depending on where they boil, you can get different fractions. Stuff like that, and these fractions are used for different things. So if it's really low temperatures that they would boil, you would use it for natural gas. As it goes up, they become less volatile. So petroleum ethers, solvents, or the gasolines usually and that's 40 to 200 range. Kerosene, jet fuel, diesel fuel. These are a little bit larger compounds, but they're still liquids. And then once you start getting into so non-volatile liquids, things like paraffin or greases. I'm sorry, mineral oil, greases, things like that, and then non-volatile solvents, which are used for like tar and asphalt and stuff like that. So one of the things about people don't realize is with asphalt roads is that the nice thing is that they're 100% recyclable, and they are. So if you go in and you get a pothole in an asphalt road, all they have to do is just grind. All they do is just grind up the top layer of the asphalt, and then melt it again, and then just relay it down. And so with a concrete road, right, you'd have to pull out all the concrete and completely relay it, put down fresh concrete. For the asphalt, you can actually go in and basically recycle it, reheat it, remelt it, lay it back down, and it's good to go. So there's one nice thing about asphalt roads. And so for their shapes, we can have two of them. First one being what's called the normal, and that's just when all the carbons are in a row or in a line like this. So you'll sometimes see this called like in normal butane or normal pentane. That just means it's in a line. But you can also have what's called branched, and just like the branches of the tree. So here's a straight line, but then there's one that there could be groups that come off of this, and so you can have a lot of branching, right? So more like so here's the main chain. Main straight chain, then you have, say, two groups coming off it, or one, or things like that. You can have a lot of branching, just like some trees are nice and straight, some are really bushy. You can have that with the alkanes as well. Okay. Now, again, for the branched alkanes, remember we were talking about this in the last chapter when we were talking about boiling point. The more compact it is, the lower the boiling point. So if we have a normal, so these are all hexane isomers, because they all have the same formula. But this one has the highest boiling point at 68. But as it becomes more condensed, as it becomes more branched, right? Notice how the general trend is it goes down. The boiling point goes down. So the melting point's a little more complicated, but boiling point's not too bad. Stuff like that. And so when we talk about these, we're going to be talking about the what is it? The what's called the IUPAC, stuff like that. So one of the problems was originally with a lot of the compounds, you have these common names. So vanillin, which is used in the flavoring for vanilla, geranol, which is from geraniums, azulene, which is the blue color in these mushrooms, as well as morphine from the opium poppy. So a lot of these things do have common names, but the problem is if you're trying to communicate in another language, if you're trying, different regions have different names for things, it's going to get really complicated in a hurry. With that, so IUPAC had to sit down and make some rules about how you name things. Okay, so the IUPAC stands for the International Union of Pure and Applied Chemistry. They're based actually. So what is it? They usually meet in, I think it's usually Switzerland or New York City, stuff like that. But their sort of administrative offices just down the street from my university in the Research Triangle Park in North Carolina. So which I always thought was really cool. But they set the rules for this, and the idea is, can we make a naming scheme such that no matter how you draw the molecule, it will have, if you draw a molecule a bunch of different ways, it will all have the same name, so that there's no ambiguity here with that. And so when we're talking about, if everybody knows the rules, when we're talking about this, when we're describing this, as when we write a paper, somebody 3 states away would be able to understand it, or 3 nations away understand it. Okay. So you'll sometimes hear this for alkanes, or sometimes called saturated, and that just means that they have the maximum number of hydrogens for them. Every once in a while you hear it called aliphatic, and that just means fat, because it's the if things are greasy, fatty molecules, they have a lot of these alkanes as part of it. So you don't hear that all that often anymore, but sometimes it pops up. Okay, so the alkanes. So we're going to be using these base names a lot. And so again, this is one of those that you need to memorize. Okay, and so if it's a one carbon group, right, it's called methane. Two carbon groups, ethane. Three carbon groups is propane. Four is butane. So the first four are really weird, and we'll actually talk about that in a second. The rest of them get a little bit, make a little bit more sense. So like pentane, so 5. Hex, 6, hexane, heptane, things like that. But notice how they all have the ane suffix, right? Because they're an alkane. Okay? So you're going to need to know. I'm going to expect you to know all the way up to 12, which is dodecane. Okay? So a 12 carbon alkane would be a dodecane. Okay? Now methane. So the prefix meth actually comes from wood. Because the original, if you distill wood alcohol, it has a one carbon group on it. It's called methanol, and so they use that as the suffix meth. For that, so ethane, I think. So this one's a little more complicated. I think it comes from alcohol because, again, the 2 carbon alcohol is the one that we drink. That we can drink with that. So I believe that's where it comes from. Propane, with that. So the prop actually comes from pro. It is the so pro is the it means first with that, and so it is what's called so it comes from propionic acid, which is a 3 carbon carboxylic acid. It's the first one that has, it's not infinitely soluble in water. And so a 1 carbon carboxylic acid or 2 carbon carboxylic acid, those are infinitely soluble in water. But propionic acid, that 3 carbon carboxylic acid has at some point it becomes becomes insoluble at specific concentrations, and so it's like the first fat. Butane, the bute from that, not but, bute, the 4 carbon trig, that's actually comes from butter. So when you get rancid butter, again, it's a carboxylic acid. It's a 4 carbon carboxylic acid that's typically produced. Since it was taken from butter, it's bute, like that. And so that's where the first 4 name come from. After that, it gets more much more regular. So with that, so the first thing we're going to have to do when we're naming these is name the longest chain, longest continuous chain of carbons. Okay. Now, typically it's going to be the horizontal chain, but it does not have to be. Okay. And so you can go up these what are called the side chains with that. So, but you need to be able to go from one side to the other. Without like going backwards or double counting, things like that. You can only count things once. And so for here, right, so here are the carbons of the main chain, right? So 1, 2, 3, 4. So here it's 1, 2, 3, 4, 5, 6, right? But you could also do, right, these right there. That'd be fine. 1, 2, 3, 4, 5, 6. So you have to be careful, right? So for here, right, 1, 2, 3, and we'll talk about when you do one or the other. 4, right? But if we go up here, right, you can go 1, 2, 3, 4, 5, right? So in fact, this is actually the main chain. So you go from one side to the other without, like you don't go 1, 2, 3, 4, 5, 6, 7, or things like that. So you go from one end to the other, just nice and smooth. And don't go backwards to that, but don't forget to go down the side chains when figuring that out. And so those carbons we're going to name as the main chain. Okay. Let me get this. Oop. Well, anyway, so if these are part of the main chain, then we have to these things that stick out from it. Here, the branches, those are called the side chains. Okay, and if we have more than one of something, one of those side chains, we're going to have to let us know. And so we're going to use this. If we have 2 of something, it'll be a di. If we have 3 of something, it'll be a tri. 4 of them will be a tetra. So you do need to know this list. with that. So not a big deal, right? So a lot of Greek and Latin roots in here. Okay. Now for the naming. Okay. So what we're going to do is for the naming of these things, you're going to see a lot of this 4-step process. Okay. So these are the steps that I go through to name something. You're going to see this a lot. You can do it if you've got a better way of doing it, fantastic. But this is the way that I typically do it, and I try to take it the same way each time. And then so all you need to do, if you know the 4 steps, then you can go in and just memorize the slight differences between the molecules. Okay, so the first thing you got to do is you've got to find that the longest, the main chain, right? The longest stretch of carbons that in a row. And don't forget, you can go down the side chain. What look like the side chains? It does not have to be the horizontal. Okay, so for that one, then you're gonna you're gonna name. Okay, so if it's 6 carbon long, it's gonna be hexane. If it's 8 carbons long, it's gonna be octane. Okay, so that is going to be the main chain. So you've named all of those carbons. With that, and so the other carbons that are branching off, those you have to name. We also have to name, but they're going to be named separately. Those are going to be named as a side chain. And so what we're going to do to designate that those carbons are part of the side chain is we're going to name those. We're going to start with those base names, and instead of having an A-N-E, methane. Instead of having an A&E suffix, what we'll do is we're going to change that to a YL. So methane becomes methyl. Ethane, right, becomes ethyl, right? Propane becomes propyl. Now you may have heard this before as isopropyl alcohol, right? That's the propyl. That. And so and so on and so forth. So if you had a 6 carbon side chain, it would be a hexyl. Okay, you just take off the A and E, right? You take off the A and E and add YL to indicate that those carbons are part of the side chain. Okay. Now now that you've got those listed, and you'll see me actually list them out. When you do that, what you can do is say, okay, now we need to determine where on the main chain they're attached to it. Is it carbon 1? Is it carbon 2? Carbon 3? Carbon 4? Whatever of the main chain. But remember, we don't have to. It's the way we draw it is going to be independent, stuff like that. And so what we need to do is we need to check to see. We need to start from the left side, and then we have to start from the right side. And you'll see. So we'll get a list, and we'll get the numbers for the attachment points. And so when we add those up, the number set that gives the lowest sum, that's going to be the numbers that we use. Okay. And then to construct the names, the side chains are going to be listed first alphabetically. Okay, with that. And now the di, the tri, the tetra, that doesn't matter. Okay, so if we have ethyl or methyl, whatever, by that ethyl will go first, and then methyl, and then whatever. The main chain is always listed last. Okay. Now for the side chain, now we have to indicate where those side chains are. So we're going to have to put the numbering to say, okay, this one's at this carbon here. We're going to put that out front, and we're going to list those in increasing order out front with a comma. Okay. So with that, so putting it alphabetical order, ignoring the number prefixes. Although you do have to be careful. We're going to be talking later about cyclo and iso. Those make a difference, but the regular ones do not. So the di, the tri, the tetra, those don't work. Okay, and so we'll put these together. I know it's kind of weird, but we're going to walk through the first one. Okay, so the first thing we do is we want to name this compound. Okay, so the first thing we need to do is we need to get find the main chain. Okay, so I'm going to put in the carbons here, just so we can see it. Okay. Okay, so if we just did the main, so we just did the horizontal, right? And you'll see me circle it lots of times. So it'd be 1, 2, 3, 4, 5, 6, 7, 8. So that would be here, right? But we could also do 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, right? So this one's 8, but this one's 9. Okay, now let's try this one. We could also do this one, right? 1, 2, 3, 4, 5, 6, 7, 8. Well, that's not going to do us any good, right? It says 8. So we're going to want to use these blue carbons here as our main chain. Okay, and so with that, right? So since we're going to be using that, so 9 equals nonane. So our main chain is going to be the nonane, not no name. I had a student think it was no name. No, it's nonane, A-N-E. Look at that. So the main chain is going to be nonane. Now we've already gotten the blue ones. Okay, we've already listed those. Right, these blue ones are included in the nonane. Okay, we've already named these. So the side chains are the carbons that are coming off of it. So it's going to be, right, it's going to be this one, and this 2 carbon side chain. Okay, so each one of these is a 1 carbon side chain. This is a 2, right? So this was originally methane, right? And we're going to take that off and add YL. This was originally ethane, because it's a 2 carbon side chain, right? So 1, 2. And so that one becomes ethane. So we have 2 methyl groups and an ethyl. Okay, and so we have this, and so typically what we'll do is we'll say, okay, I've got, right, so we have methyl, and ethyl. So if we start on, so we don't know which side is going to be carbon 1, right? Put in the dots so it's easier to see. 1, 2. If we started at this end, right, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this methyl group would be hanging off of carbon 3. This one would be hanging off of carbon 5. This one would be hanging off of carbon 6. Now, if we did it the other way, if we said this was 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's really bad, 9, sorry. Now this one, the ethyl group is hanging off of 4. This one would be hanging off of 5. And then this one would be hanging off of carbon 7. Okay? So when you add them up, right? So this one would be, let's see, that's what, 8, and then, so this is 14. These guys here, right, that's 12. This is 16. Notice how these add up to a lower number than these, and so these are the numbers that we're going to be using. Okay? So we're going to be using these numbers here. Okay, so put them in alphabetical. So ethyl comes before methyl, and then the main chain is going to be at the end. Okay, so ethyl comes before methyl. Now, and then specify the number, right? So we have one of them is at the ethyl is at carbon 6. Okay? We have a methyl at carbon 3, methyl at carbon 5. Okay, all right, 1, 2, 3, 4, 5, 6. Okay, now these we can combine, okay, into dimethyl, right? Because otherwise it's going to be 3-methyl, 5-methyl. It's going to be hard. It's easier to say 3,5-dimethyl. Okay, and then we're going to construct the names. And notice how the di doesn't matter, right? It's just methyl versus ethyl. Okay, so we're going to put where so we have the main chains listed alphabetically, ethyl, methyl, with the position numbers out front of each one, right? So, and then the main chain at the end. Okay, and so what saying is we have a main chain that's 9 long, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 2 methyl groups, right? Where are they? Well, one of them is hanging off of carbon 3. One of them is hanging off of carbon 5. We also have an ethyl group, right? 2-carbon ethyl group. Where is that hanging out? That's hanging off of carbon 6, right? 1, 2, 3, 4, 5, 6. Okay? And there we go. There's our name. We have a lot of examples to go through. So for this one here, right? So we can put in our carbons, right? I do like the dots because it makes them a little bit easier to see. Okay, so the first thing we need to do is we need to find the main chain, right? So when in doubt, start with the horizontal. So 1, 2, 3, 4, 5, 6, right? But we can go down those side chains too. 1, 2, 3, 4, 5, 6, 7. Oh, hey, and then we can also do 1, 2, 3, 4, 5, 6, 7. Now, when you've got a choice to make, okay, when you've got two of these, IUPAC says that it would prefer to have more smaller side chains than one big side chain. Okay, so if we look here, so if we were to take this as our main chain, right, we would have methyl, 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 methyl. Okay, if we were in fact to go up there, we would still have 4 methyl groups. So in this case, it doesn't really matter. Okay, we'll give an example of when it does in a minute. Okay, so so for the main chain, right, it's going to be 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to do that just out of convenience, mostly horizontal, but it wouldn't really matter in this case. 1, 2. So C7, right? So that would be heptane. Okay, so the side chains, right? We have 4 1-carbon side chains. Right? So it'd be methyl, methyl. And so you just list them out. Just list them out individually. Okay, and so we need to do we need to deal with the numbering. Okay, so we got to start on this side. So 1, 2. Oops. Make it different colors so it's a little bit easier to see. So 1. Come on. 1, 2, 3, 4, 5, 6, 7. Okay, so we have a methyl group hanging off of carbon 2, carbon 3, carbon 4, and carbon 5. Right? If we were going to go the other way, right, it would be 1, 2, 3, 4, 5, 6, 6, 7. Okay, so here we would have 3, 4, 5, and 6. And so if we add them up, right, so this is 5, right, this would be 14. And so 6, this would be 18, right? So we're going to use these numbers here. Okay? And so we have 4 methyl groups, right? So we can smash those all together, and so it becomes tetramethyl. Right? And then we have 2, 3, 4, 5 tetramethyl, right? And then the main chain at the end, heptane. Right? If I have a tetra here, I have to have 4 numbers out here, even if they're the same number. Okay? If I have a tri out here, I have to have three numbers. If I have a di out here, I have to have 2 numbers. It drives me insane how many students will just put, if it's the same number, they'll only list it once. If it's a di, it drives me nuts. Okay, but here's the name. Okay. So hey, we got it right. Okay, and so for this one, right, we'll do the okay, and so it's going to go 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. In this case, it doesn't matter. And no matter which one of those you choose, you're going to end up having 3 methyl groups. And so, just out of convenience, let's just do the horizontal. Okay, so that'd be C8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So that would be octane. And again, we're going to do, we have these 3 methyl groups. Okay, so methyl, methyl, methyl. And so, right, and so we need to do the numbering. One thing I don't think I mentioned is that with the side chain, right, it's not going to be here and here, right? We've already named that carbon there. That's part of the main chain. It's the things that are not part of the main chain. Those are the part of the side chain. So you can't be part of a side chain and a main chain. You're either one or the other. Okay. So for this one, right, for the numbering, right, we're going to start on the left, right? So we'll go 1, 2, 3, 4, 5, 6, 7, 8. All right. So we have a methyl hanging off at 2, 6, and 7. If we go the other way, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it becomes 2, 3, and then 7. Okay, so we add them up. All right, so this is what? This is 15, and this is 12. Right, so in this case, we're going to be using those numbers. So again, so they're all methyl, so it doesn't matter. So we're going to smash those together as trimethyl. Right? And so we're going to use 2, 3, 7. So we go in increasing order. Okay? Trimethyl octane. So for the number, to separate numbers, we usually use a comma. And to separate a letter and a number, we usually use a dash. There's a bunch of different ways you can do this between letters. So like the methyl and the octane, the trimethyl and the octane, you can put a space. I typically do, just so it's a little easier to see, but sometimes you don't need it. I'm sure there's a rule somewhere, but in that case, that doesn't really much matter. It's more of a personal preference. So it could be trimethyl octane as all one big word, or you can have trimethyl and then octane be 2. That doesn't matter. Or you could put a dash in there. Who cares? So, good job. Okay, so for this one, right, let's put in our carbons. Remember that that's the intersection of lines, right? So there's a carbon there. So we need to do the main chain, right? So it's going to be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, 6, 7. Oh, crummy, there's going to be 2, right? So that you could have this, right? Or you could have the horizontal. Okay? If we do the red, okay, we're going to have methyl, methyl, ethyl as a side chain, as side chains. If we do the blue, right, all we're going to have is this one giant group here. IUPAC says we'd rather have more smaller side chains than one big side chain. Okay? So what we're going to need to do is we're going to need to use this guy here. Okay? So we have methyl, methyl, ethyl. Okay? And so for this one, right, 1, 2, 3, 4, 5, 6, 7. So C7. So it'd be heptane. Okay. And so for the side chains, right, we have methyl, methyl, ethyl. And you're like, wait, hold on. Why isn't that why isn't that an ethyl? Well, they are. I mean, well, it's not, I should say. This is the ethyl group. The carbons have to be attached directly. So there's the main chain in between it, and so these act like two independent methyl groups, right? So if it was here or if it was there, right, they're acting as independent groups. This one right here, because they're directly attached to each other, this one's the ethyl. So we're going to have two methyl groups, methyl, methyl, and this ethyl group. Okay? And so if we look at the numbering, right, we got to start at one end or the other. Right? So we're going to do 1, 2, 3, 4, 5, 6, 7. Okay? And so for this one, right, each one of these is going to be at 2. Right? Each one of these methyl groups is hanging off of carbon 2, and the ethyl group's at 3. Right? If we go the other way, 1, 2, 3, 4, 5, 6, 7. Right? Each one of these methyl groups is hanging off of carbon 6. the ethyl groups are hanging off of carbon 5. So if you add them up, right, so this is 7. This one is 17. Right, so we're going to want to use these numbers. So when we put this together, right, ethyl comes before methyl, so it becomes 3-ethyl. We're going to combine those together for dimethyl, so it's going to be 2,2-dimethyl. And yeah, it's the same number, doesn't matter. I've got a di here, I better have 2 numbers out front. And then at the end, heptane. So there's your name. Okay, so you can have, because of course things can't be quite that easy. So you can have more complicated side chains, and starting particularly at the propyl group, right? So each one of these side chains is connecting, is 3 carbons long, right? So 1, 2, 3, right? 1, 2, 3. But this one, oops, I should probably, let me start again. So this is this little squiggly line. That's where it's connecting to the main chain. Okay, and so for this one, it's connecting through carbon 1 to the end. This one, however, it's connecting to the main chain through carbon 2. And so we need to be able to distinguish these two. And so this one we just designated as a regular propyl group, because it's connecting through one of the end carbons. If it's connecting through one of the middle carbons, it's the isomer of a propyl group, so we call it isopropyl. Okay, so with that, so we can also call it a 2-propyl. I think this is an easier name than isopropyl, because what it's saying is we're connecting to the main chain through carbon 2. And so that's what that, so you'll see this listed as well. So, but for this one, you can use either one. Butyl becomes more complicated, right? So again, all of these are going to have 4 carbons. People typically don't use isobutyl or secbutyl all that often. However, they do use the tert butyl or tertiary butyl, or just T-butyl. This one comes up all the time. Okay, and so what you're going to need to know, you're going to need to know this guy. You know how to do either one of those, or the T-butyl. Okay, the technical name would be 2-methyl-2-propyl. So it's a methyl group hanging off of a 2-propyl group. It's a methyl group hanging off of carbon 2 on a 2-propyl group. It's like that. So, but usually T-butyl. So T-butyl comes up a lot. And so that one you do need to know. I wouldn't worry too much about isobutyl, secbutyl. They don't come up all that often, and usually people just have to look it up anyway. So definitely no butyl. Okay, so like we mentioned before, sometimes you could just designate any sort of alkyl group, any sort of alkyl side chain, any sort of side chain like this as an R. That just means it doesn't matter. That's not the important part, so we're just not going to worry about that. And so methyl, ethyl, propyl, isopropyl, butyl, T-butyl, hexyl, whatever, it doesn't really matter. When that's the case, then we'll do an R. If you saw the R prime, that just means it's a different R group than this. So like one side could be propyl, the other side could be hexyl. Doesn't matter. So how about that? So just like with the halides and with the alcohols, with that. So if we can classify hydrogens depending on how many the carbon that is attached to. So this is going to be a primary hydrogen because its carbon only has one thing attached. Just like this one. This carbon only has one carbon directly attached. This one is a tertiary, right? This carbon is tertiary because it has 1, 2, 3 carbons attached. This one's secondary, right? Because this one has 1, 2 carbons attached to it. This one's primary, right? Because this one only has one carbon attached. So it's no different than for hydrogens. It's no different than alcohols or halides. Look at the carbon, how many other carbons are directly attached to it. That's going to say if it's a primary, secondary, or tertiary. The hydrogen, again, it's going to be an issue of reactivity in later reactions. Okay. Now you can have a halide as part of as a side chain, and so for that one, what we're going to do is we're going to take the INE off. So fluorine, right? We're going to take off the INE and just add O. So fluorine becomes fluoro. Chlorine, chlorine becomes chloro. Bromine becomes bromo. Iodine becomes iodo. Okay, and they don't need. So we'll talk a little bit more about priority groups, stuff like that. They're listed like every other side chain. They're not given any sort of priority. So they're treated just like methyl group, ethyl, whatever, stuff like that. So it's just they're gonna have a slightly different name. Okay, so if we had this one, right, so let's put in our carbons. Okay, so if we did the main chain, right, so we did the horizontal, it would be 1, 2, 3, 4, 5, 6, 7, 8. Okay, if we did down the side chains, right, 1, 2, 3, 4, 5, 6, 7, 8, right, or we did 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this one here, if we did this one around here, right, we would have a methyl group, a methyl, a fluoro, and this isopropyl group here. If we did this one here, right, we would have a methyl, a fluoro, and isopropyl. So in that case, it's not really going to matter. So just out of convenience, let's just do the horizontal. This is 1, 2, 3, 4, 5, 6, 7, 8. So C8 it becomes octane. Okay, and so the side chains then becomes methyl, isopropyl, or fluoro. And so we're going to do it. So it's independent. So you can either have, right, so we're going to have a methyl and either an isopropyl or this 2-propyl group. Okay, and then we're also going to have the fluoro. Okay, and it's not going to matter, well, you can use either one, but it's going to make a slight difference on the naming, which one you use. Okay, and so if we're going to use, so we've got our side chains, right? Now we need to get the numbering. So for this one, right, so we need to start on the left side. So 1, 2, 3, 4, 5, 6, 7, 8. So the methyl's hanging off of carbon 2. This isopropyl or 2-propyl group is going to be at 3, and the fluoro is at 6. If we go the other way, right, so 1, 2, 3, 4, 5, 6, 7, 8. Right, so the fluoro's at 3. The isopropyl 2-propyl group is going to be at 6, and the methyl group's at 7. Right, so if you add them up, so this is 9, this is 11. This one is 16. Right, so we're going to use these orange numbers here. Okay, so if we use, so let's do the isopropyl first. So for this one, it's going to be methyl. The iso, so isopropyl, the iso and isopropyl makes a difference. So from ethyl, isopropyl, fluoro. So if we're going to use those names, right? So isopropyl fluoro comes first, right? So it's going to be 6 fluoro, and then isopropyl comes before methyl. So then it's going to be 3 isopropyl, and then 2 methyl octane. Now, if you were going to use, instead of isopropyl, you would use the 2-propyl. Now, right, so again, fluoro is going to be first. So it's going to be 6 fluoro. Now for this one, you're comparing methyl to propyl. So for this one, the methyl would come first. And so for this one, it would be 2 methyl. And then 3, and then just bolt in 2 propyl. And then octane. So you can use you can use parentheses in here, and I like to do it especially with the 2-propyl. I will just say, like, it's a 2-propyl group. Where's it hanging off? Carbon 3. So 2-propyl is kind of a bit of a mouthful. Now, don't put 2,3-propyl because I wouldn't know what that means. Or it just means you've got 2 propyl groups in there. But it's a 2-propyl group hanging off of carbon 3. You can use either one. It's just whichever ones you're comfortable with. But either one will do. Either one is perfectly acceptable. Okay. So, there you go. Okay, so for alcohols, okay, so these are ones that have OHs in them. So for that, so for alcohols, what we're going to do is we're going to indicate that it has a alcohol in it by replacing the main chain name with the OL. Okay, so methane becomes methanol, ethane becomes ethanol, propane becomes propanol, butane becomes butanol, things like that. But the main chain has to contain the alcohol group. Even if there is a longer chain somewhere else, it has to have the alcohol group in it because the alcohol has priority. Okay, and we're going to name and find all the other side chains that are in there, and then we're going to get the numbering. Now, the numbering it makes it a little bit easier because the end that has the ends closest to the alcohol is going to be carbon 1. You don't have to do the back and forth thing. Okay? But we do need to know, so you'll see me list alcohol in quotes because we are going to need to know the number where that alcohol is. Is the alcohol hanging off of carbon 1, carbon 2, carbon 3, carbon 4, wherever? It's going to make a difference in the reactivity of the molecule. So we need to indicate that. And then you put the stuff out as normal. Now, with the alcohol, with the parent chain at the end, there's 2 ways that you could do this. So if we had, say, a 3-hex, so if the alcohol was at 3, we could either list it as 3-hexanol, where we're going to say the alcohol is hanging off of carbon 3, or that's the older method. We could also just put it right next to the OL and just indicate it hexan 3-ol. Okay. This is the newer method of doing it, and you'll see why once we start combining functional groups, why you'd want to do that. So with that, but I don't care which one you use. You can use either one, okay, for the main chain. But we do have to say where that alcohol is. We don't write alcohol in the name. So with that, that's what the OL is for. So say that we've got the alcohol there. Okay. And so for this one, right? So with that, so we have one. Put in our carbons. 1, 2, 3, 4, right? So we do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, so this is going to be our main chain. It has the alcohol in it. So hexane becomes hexanol. Now if we're going to have, so for a side chain, right, we've got that methyl group there. We're going to include the alcohol in there in quotes because we need to figure out, is it hanging off here, 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 here? Where is it hanging out? Okay. So for this one, right, the end's closest to the alcohol. So in this case, it would be this one, right? 1, 2, 3, 4, 5, 6, right? So the alcohol would be hanging off of carbon 3, and the methyl would be hanging off of carbon 4. So to put this together, it would be 4-methyl, 3-hexanol, or you could write it as 4-methyl, 3-hexanol. You could do it either way. I don't mind. Now, you could have more than one alcohol in it, but again, the main chain is going to have both of those in there, and we need to indicate that it's got 2. Okay? So for this case, right, again, the main chain is going to be right here. So it's 4 carbons long, so as butane becomes a butanol. So we have the 2 alcohols. We need to let people know where they are, okay, as well as that methyl group there. Oop. You do that in blue, so it's not confusing. And the main chain is here. Okay, so we have an alcohol. So since this end is the end that has close to the alcohol, the first alcohol, so 1, 2, 3, 4. Right? So we have an alcohol hanging off carbon 1, alcohol hanging off carbon 2, and then a methyl group at 3. Okay, what we do is we say, okay, 3-methyl butane 1,2-diol. Right? That means we have 2 alcohols, and I better have 2 numbers out here. Okay, the other way that you could do it is 3-methyl 1,2-butanediol. You could also do it like that. Or okay. Now ethers, this is where we've got, the carbons on either side of the alcohol. So for this one, it gets a little more complicated, because what you want to do is you want to take where the oxygen is, and you want to split it like that. So you look on this side, see which has a larger carbon side, and so this one is 3 carbons. This side has 3 carbons. This side has only 1 carbon. So this is going to be your main chain, and this one, this side becomes your side chain. And to indicate, so that becomes your side chain. It's a 1 carbon side chain, but you're connecting through the oxygen, and so instead of putting methyl, we put methoxy. Okay, and so this one here, again, you've got propane, and then you've got a 1 carbon side chain that connects through the oxygen, so that becomes methoxy. Here you've got your ring here, so it's a cyclohexane, which again we'll talk about that in a second. So your side chains are going to be here and here. So again, it's a 2 carbon side chain, right, which would normally be methyl, but you're connecting through an oxygen into that main chain here, and so it'd be ethoxy. So it's a 1,4-ethoxy. So we have this one. Oops. So we have the carbons here. We split this, right? We have a 1, 2, 3, 4, 5, 6, 7 carbon side on here, and we only have a 2 carbon side on this side. So that makes this a side chain, along with the fluoro. So we've got a fluoro side chain, and then it's a 2 carbon side chain, but it's connecting through the oxygen, so it becomes ethoxy. Okay, the main chain, right, is 7 long, right? So it's normal alkane, so it's hexane, or excuse me, heptane. And then for this one, right, so we've got, for the numbering, oops, right, we're going to go 1, 2, 3, 4, 5, 6, 7, right? So the methoxy is hanging off of carbon 3, right? The fluoro is at 4. If we want to do the other way, right, we need 1, 2, 3, 4, 5, 6, 7, right? So fluoro is at 4, methoxy is at 5, right? So if we add them up, so this is 7, that's 9, so we're going to use these numbers here. Now, ethoxy comes alphabetically before fluoro, so it's going to be 3-ethoxy, 4-fluoro, heptane. Like that. Good job. Okay, so main chains. Okay, so they don't always have to be linear. Okay, they can be go around in a circle, or we usually call it a ring. Okay, so for here, right, so it's still right, so it can be anywhere from 3 on up. Look at that. So, right, so your carbons are going to be here. But to distinguish this from a regular hexane, or a regular pentane, or a regular butane, or a regular propane, we're going to indicate that with a cyclo, and you'll hear me call these as rings, and it doesn't matter if it's a 3-membered ring, 4-membered, 5, 6-membered ring. It doesn't matter. Okay? So they're all considered rings, but they are cyclic because they come back onto each other, onto themselves. Now for this one, the first thing we're going to have to do is examine the structure and to say, okay, if is the which is longer, the longest side chain, or the longest linear chain, or the ring, the number of carbons in the ring. Now, one of the things is the carbon is either part of the ring or it's part of the straight chain. With that, so you can't be both. You can't mix and match. Okay. So with that, so if the ring is bigger around than the other one is long, then the ring wins. Okay. And then so to indicate that, since it's an alkane, right? So it would be normal sort of propane, butane, whatever. But to indicate that it's a ring, you would put the cyclo prefix out front. If, however, the alkyl chain is longer, then you name it just like a normal alkane, and now the ring becomes a side chain. So if it's a 6-membered ring, right, it would become instead of cyclohexane, it would be cyclohexyl, right? Just like methane becomes methyl. A cyclopropyl group or cyclopropane group becomes cyclopropyl. A cyclobutane becomes cyclobutyl. Just normal rules like that. Okay? We're going to do the right. So we're going to name our side chains. Now the attachment points. This is the issue because we don't know where it starts. Right. Since it's a ring, goes around. Where is carbon 1? And so what we need to do is we need to find. We still need to find the lowest number set. Okay. And so what we're going to do is we're going to give every carbon that has something attached to it on the ring is going to have a chance to be carbon 1. Okay. And a hint is that if you're starting 1, what you're going to want to do is you can go clockwise or counterclockwise, doesn't matter, as you're doing the numbers, but you're going to want to go towards the nearest side chain neighbor and then just keep going. Okay, whether that's clockwise or counterclockwise. Okay, the exception. So you pick the lowest number set. The exception is if there are two identical number sets or identical ways that you can do the numbering, and there's no other way to break the tie. Okay? So there's two number sets, there's no way to get an even smaller number set. Then what you do is you say, okay, the first side chain alphabetically gets the number 1. Okay? So so they just had to make a rule, and that's what it ends up being. Okay, and then you construct the name as normal. Okay, as you would do any other alkane. Okay? So for this one, right? So we'll put in our carbon groups, or put in our dots. Okay, so we have our ring here, 1, 2, 3, 4, 5, 6, and then we've got our linear chains, 2 carbon, 1 carbon, 1 carbon. Now notice how this does not go into the ring. You're either part of a straight chain or you're part of a ring. You cannot mix and match. Okay, and so the ring is 6 carbons, right? The longest one here is 2, so the ring wins. And so in that case, right, so C6, which would normally be hexane, but since it's a ring, the main chain is a cyclohexane. Okay, that means that the side chains are methyl, right? This methyl, that ethyl, and then this methyl down here. Now we don't know which one's carbon 1, and so we're going to give everybody a chance to be number 1. Okay, and so if we want to do, say so first off, we're going to give this one, come on, chance to be number 1. So the nearest side chain neighbor is here, and so we're going to want to go that way. So 1, 2, and then just keep going around. So 3, 4, 5, 6. And so that would make the numbering 1, 2, and then 4. Right? If we wanted to do this one, say that carbon 1, now the nearest side chain neighbor is over here, because this is only 1 away as opposed to this one's 2. So we'll want to say that's 2, and then keep going around. 3, 4, 5, 6, 7. Oop, oop, oop. Okay. So that makes this be 1, right? This be 2, and this one is 5. This one will be 5. Okay, and then lastly, right? So, right, if we give this carbon the chance to be 1, the nearest side chain neighbor is actually here. So we're going to want 1, 2, 3, and then just keep going around. 4, 5, 6. Right, so for that one, it'd be 1, right, 3, 4. Okay, and so let's add them up. Okay, so notice how everybody's given a chance to be number 1, right? So for this one, right, it's 7, right? This is 8, and that's 8. You'd say, oh, there's a tie. No. There's not a tie. We have one that's even lower. It's only if you, right? So that if you can't find anyone that's lower, right? So this one is the lowest number set. So we're going to use these numbers here. So ethyl comes before methyl. So when we put the name together, right? So it's going to be 2-ethyl. Right? We have 2 methyl groups, one at carbon 1, one at carbon 4. Right? 1, 4, dimethyl, cyclohexane. There we go. Which is that in a minute. Okay. So for this one here, right, so we've got 1, 2, 4, 5. Like that. So we've got the ring here. Now, I was going to say that's 5 around, but we also have this one. 1, 2, 3, 4, 5, 6. Uh-oh. 1, 2, 3, 4, 5, 6. Okay, ooh, now which one of these do we do? Well, we're going to want to do this one here. So we have a methyl group, and then this side chain here. If we were to go up, we just have one big side chain here. Okay? And so, let me do some blue. So our main chain is actually going to be in blue here, and so that makes our 2 side chains here. So the main chain, right, is going to be 1, 2, 3, 4, 5, 6. So C6, so it'll be hexane, right? Because we're just going to name it as an alkane because this long chain is larger than this is around, so this gets the priority. So that makes our side chains, right? So this one is methyl, no big deal. Well, what about this? Well, normally it would be a cyclo. Oops, It would be a cyclopentane, right? But just like we had methane becomes methyl, ethane becomes ethyl, we're going to have cyclopentane become. I'm going to take out the A and E and add YL. Okay, so cyclopentane becomes cyclopentyl. Okay, and so if we're going to do the numbering, right, we need to do one way or the other, right? 1, 2, 3, 4, 5, 6. So the cyclopentyl's at 1, and the methyl's at 2. And if we do the other way, right? 1, 2, 3, 4, 5, 6. Right? So we have what? 5 and 6, right? So 3 versus 11. So we're going to use these names. And again, notice how we didn't go into the main chain and then in around in here. No. Straight chain or ring. Can't be both. Okay? So for this one, right? Methyl versus cyclopropyl, okay? Because we've listed it here, that's part of the that means it's eligible with the with the alphabetical. So cyclopropyl is going to come before methyl. So we're going to use 1 cyclopentyl, 2 methyl hexane. There we go. Okay, so there we go. Okay, so for this one here, right, we're going to put in our carbon chains, or put in our dots for our carbons. Right, so our ring is going to be right here, okay, and then our linear chains are going to be here and here, okay. So the ring is 4 carbons around, and our longest linear chain is 2 carbons long, so that means the ring wins. And so for this one here, so C4, right, it would normally be butane, right? But since it's a ring, it becomes cyclobutane. Okay, so our side chains are going to be methyl and ethyl. Okay, so we're going to give this guy, this carbon here, a chance to be number 1. So carbon 1, our nearest side chain neighbor is here, so this will be 2, and we're just going to keep going around. 3, 4, so it becomes 1, 2, and then we're going to give this carbon a chance to be number 1, and then the nearest side chain neighbor is here, so 2, so 3, 4, and we just keep going around, so it becomes 1, 2, and so they're both 3. And there's no other, the problem with this one is that there's no other way that we can break this tie. There's no other smaller number sets that we could figure out. Okay, so IUPAC says, okay, we need to make a rule. We're going to say, okay, the first alphabetically, so ethyl comes before methyl alphabetically, so it's going to get the 1. So we're going to use those right there. And again, it's a very, very special case. Okay, so it becomes 1 ethyl, 2 methyl, cyclobutane. Okay. So, there you go. Now for alkenes, all right, so for these, this is where we have a carbon-carbon double bond. And just like with the alcohol, the longest chain needs to contain the unsaturation, the double bond, the carbon-carbon. So this just means the carbon-carbon double bond. Okay. Now for here, the alkene, we're going to change the A&E suffix for the main chain to E&E to indicate that there's an alkene in there. Okay. All the rest of them are going to have the YL suffix with that. So, and again, I'm going to include alkene in our list of side chains because we need to again determine the attachment point where that alkene starts. Okay. So for that, so we're going to do the numbering just like with the alcohol. The double bond has priority. So for that, and so the N that's closest to the start of that double bond, that becomes the carbon 1, and you go from there. And just like with the alcohol, you put all the side chains out front. The E&E suffix here indicates that there's the alkene, and so you can put the numbering either in the front of the main chain or right next to the E&E, just like with the alcohol. Okay. So for this one, again, we're going to have our carbons here. Right, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, so we're going to use this guy here. All right, so 1, 2, 3, 4, 5, 6, 7, 8. So C8, right, which would normally be octane, right? But since we have a double bond, it's octene. Okay, so our side chain then is this guy there. So we have an ethyl group, but we also have this alkene that we're going to have to deal with as far as the numbering, say where it starts. Okay, and so with the with the numbering, right, we're going to, this end here is closer to where the alkene starts, and so that's going to be carbon 1. So 2, 3, 4, 5, 6, 7, 8. Okay, so the ethyl's hanging off at carbon 5, and the alkene starts at carbon 2. So if it starts at carbon 2, the assumption is the other end of the double bond is going to be carbon 3. Okay, and so for this one, so with that, so it's going to be 5 ethyl, 2 octene, or you can write it as 5 ethyl oct 2 ene. You can do either one, whatever you feel comfortable with. Okay. Notice I did not write octene or alkene in here. That's what the E&E is for. Okay. It starts at carbon 2, so it goes from 2 to 3. Okay. So here, right? Okay, so we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay, So this is going to be our main chain. Right? So C7, which would normally be heptane, but because we have a double bond in there, it's going to be heptene. So that guy there, right? So we have the methyl, and then we also have the alkene. Right? We have to say where it starts. Okay, so for this one, right, this end is closer to where the alkene starts, right? So we're going to have the big number 1. So 2, 3, 4, 5, 6, 7. So the methyl is hanging off of carbon 5, and the alkene starts at carbon 1. Okay, so it goes from 1 to 2. So we're going to indicate that it starts at 1. So it's going to be 5 methyl, right? 1 heptene, or you can write it as 5 methyl hept 1 ene. Either one, I don't care. Now you can have cyclic alkenes. Okay, so about that. So for that one, it's going to be just like any other alkene, but again, the ring is going to be the main chain because that has the double bond as part of it. But we have to indicate, just like with the cycloalkanes, with the cycloalkenes, we're going to have to put that cyclo prefix out front. Okay, and we're going to need the E and E suffix out, at the end because they indicate that there's a double bond. Now again, so the alkyl chains, but this one it ends up being a little bit easier because the double bonds, the unsaturation. This is the C carbon-carbon double bond. Carbon 1 and carbon 2 are going to be the carbons of that double bond. Now you don't know if you get to go clockwise or counterclockwise through it, but that's the easiest way to do it. So we're still going to get the lowest number set, but carbon 1 and carbon 2 are going to need to be that double bond. Okay, and so we're just doing normal. Now this one we don't technically have to put the 1 out front. You can do it, and I would encourage it, while you're still learning. But because it has to be at carbon 1, we can get away with not putting it in there. It's one of the few times you can assume stuff like that. You don't have to put 1 cyclohexene because everybody knows that's where it has to be. Okay? But again, I would encourage it. So, okay, so here's our carbon, so put in our dots. Okay, so for this one, right, so this is going to be our main chain, right, because it has the double bond in it, it's the ring. So that means that this guy, put that in blue so it's easier to see. So we have that 2 carbon side chain and that 1 carbon side chain. So we have an ethyl and a methyl, and then we also have the alkane we're going to have to deal with, or alkene, excuse me. Okay, so what we're going to do is we're going to say, okay, if this is going to be carbon 1, so that means this one has to be carbon 2, and then we have to keep going around. So 2, 3, 4, 5, 6. Okay, so this will obviously be 1, and this would be 3, 4. If we went the other way, right, it would be 1, 2. So if we went 1, 2 like this, and keep going around, 3, 4, 5, 6. Right, so again, this would be 1, but then this one would be 5, 6. So we add them up. Right, so 8 versus 12. So we're going to use these green numbers here. So it ends up being, right, ethyl comes before methyl, so it's going to be 3 ethyl, 4 methyl, we never did this, so hexene, right, so the main chain, right, C6, which would be hexane, right, it's a ring, so it's cyclohex, but it has a double bond in it, so it'd be ene. Okay. See, like that. So that's fine. You could put the 1 out here. You could put the 1 in front of here. That's fine. Or just in this case, you don't have to put the 1. Okay. Alkynes are going to be the exact same as alkenes, something like that, except you have the YNE suffix instead of the ENE suffix. But otherwise, it's going to work exactly the same as an alkene. Okay. So if we have this one here, But again, we're going to have to make sure that this triple bond is part of the main chain. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Yeah, okay. So this ends up being the main chain. All right, so 1, 2, 3, 4, 5, 6, 7. So C7. Right? Normally be heptane. But since there's a triple bond in there, it becomes heptyne. Okay, so the side chain, right, it's going to be this guy here. So it's either going to be an isopropyl or a 2-propyl. And then we're also going to have to include where that alkyne starts. So carbon 1, carbon 2, carbon 3, wherever. Okay. So again, the end that closest to where the alkyne starts is going to be carbon 1, so the numbering has to start 1, 2, 3, 4, 5, 6, 7. Okay. And so when we put the name together, right, so we're going to say like 4 isopropyl, and then 2 heptyne, or you could say 4 2-propyl, hept2-ine. Now you can mix and match. You know, you could do 4 isopropyl hept2-ine, or you could do 4 2-propyl 2 heptyne. It doesn't really matter. Stuff like that. So as long as you've got those elements in there, you're good. Okay. Now you can have double and triple bonds, or multiple double bonds, triple bonds in there. And again, if you're going to do that, just like when we had the multiple alcohols, you would have to say like diene or diine or triine, or things like diine or diene, triene, things like that. So just like that, and you're going to have to indicate where each one of these starts. So this one starts at 1, this one starts at 3, so it's 1, 3 diine. This one starts at 1, this one starts at 4. Doesn't really matter which way you go. So it's a 1, 4 diine. Right, so this one starts here, 1 to 2. This one starts here, 2 to 3. Right, so 1, 2, 3. Right, so it's a 1 for this one, and then 2 for this one, diene, like that. So now, if you have mixed double and triple bonds, it's the double bond that gets the priority. Double bond gets the priority. Okay, so you're gonna have to you're gonna have ene, stuff like that. And so for this one here, right? So here's our carbons, right? So it's 6 long, so it's hex, right? One ene, right? So it starts at 1. 4 ine starts here. So this is why you could technically do 1 hexene, because this indicates that, and then this indicates that. But this is where putting it next to that functional group name helps. Stuff like that kind of keeps it a little straight. Although it's a really crazy name, stuff like that. But you can do either way. So if we got this one right, so 1, 10. Okay, so our main chain is going to have the double and the triple bond in it. So it needs to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you can say, wait, hold on, why can't you just do this? Well, you have to have the whole alkene in it. Okay, you can't just do a glancing blow with this one here. So it's got to be this guy right there. You can't just have one carbon of the double bond or triple bond in your main chain. So for that, you have to have both of them. So it becomes 1, 2, 3, 4, 5, 6. So C6, which would normally be hexane, but ours is going to be hexene, ine, kind of craziness. Okay, you do the best with the spelling. Okay, so our side chain is going to be here, right? So it's ethyl. But we're also going to have the alkene. Where does the alkene start? And where does the alkyne start? Now for this one, again, the double bond gets the priority, so it's the end closest to the double bond. So it becomes 1, 2, 3, 4, 5, 6. So that the ethyl's hanging off of carbon 3, The alkene starts at carbon 2. The alkene starts at carbon 5 or carbon 4, 4 to 5. So if you add those up, right, it's well, not that it meant you don't have to add them up. That's what it has to be. Right. So the ethyl, so it becomes 3 ethyl, and then hex to N or ene for yne, or you could put it as 3 ethyl 2 hexan 4 yne. Just do the best with the spelling that you can. Like that. So to indicate that, yep, there's this, 6 long, there's a double bond, there's a triple bond in it. Right? Where's the double bond? It's a carbon 2. Where does the triple bond start? Starts at carbon 4. And oh, hey, there's an ethyl group in here, carbon 3. So sometimes, so just as as an aside, you'll sometimes hear them say double bonds, particularly the alkenes, referred to as olefins. That's again a Latin combining to make oil. So all it means is that it's a double bond. Again, you don't hear about it that often, although you hear about it as what's called olefin metathesis, which is a type of reaction where you're putting 2 carbon bond molecules together. Kind of a neat reaction. But anyway, that's where you mostly hear about it. But again, it doesn't come up all that often, but sometimes you'll hear it. See it in literature or hear it spoken about, and it just means a carbon-carbon double bond, an alkene. Now you can have, because remember with the alkenes, you cannot get free rotation around this because remember the pi bonds have to be in alignment, and so if you're trying to do a rotation, you're going to have to break that bond. And so what you want to do is you want to look at the carbons that are on this, and lots of times you'll have a hydrogen on either side. If those hydrogens are pointed in the same direction, away from the double bond, we call that the cis version of that double bond. If they're pointing in the opposite direction, so it's the trans. So they'll either both be up or both be down if they're cis, meaning same, or you'll have one up, one down for the trans. So this would be the cis alkene, and this would be a trans alkene. They're going to have slightly different properties. And again, we'll go into this more later, but just be aware of these. Okay? Typically, the trans version is going to be more stable than the cis, so that because of crowding. It's what's called sterics, right? So hydrogens are really tiny, and so you would have the big groups. If you have the big groups right next to each other, right, you're going to get crowding. If it's the trans version, right, because this is up and down, right? These are both down. So this is the cis, this is the trans, right? You're going to have big group next to little tiny hydrogen, big group next to teeny tiny hydrogen. So this is going to be more stable. Okay. The big exception is the cyclic ones, and so with the cis is almost always going to be more stable, right? Because here the hydrogens are pointed like this. Here in the trans version, it's going to look like that. This is as small of a ring as you can get with a trans double bond. And actually, I've got this in the lab, and it's incredibly reactive. So with that, see it to be the cyclics are almost always going to be cis. Okay, so degree of unsaturation. So one of the ways that we can do this is if we're looking at a formula, okay, we can kind of tell a little bit of structural information about it. Okay, the older name is degree of unsaturation. Okay, the newer version is index of hydrogen deficiency. That's a little bit harder to say, so I just keep saying degree of unsaturation. What this is saying is that so if unsaturation, you don't, if it's saturated, maybe that's a better way of saying this, you have the maximum number of hydrogens you could have on the molecule. Okay, so ethane, right? This is the maximum number of hydrogens, so it's C2H6. It's the maximum number of hydrogens. We call that saturated. If instead there's a double bond, right? Notice how we've removed 2 hydrogens, Okay, and it turns out rings do the same thing. For every ring you've got 2 fewer hydrogens on there. So about that, and so we can get a little bit of information about the molecule if we run if we calculate the degrees of unsaturation. So what that tells us is how many rings and how many pi bonds. Now, the bonds, the pi bonds could either be carbon-carbon double bonds, but they could also be carbon-oxygen double bonds, or carbon-nitrogen double bonds, or oxygen-phosphorus double bonds. It doesn't matter. So that doesn't matter. Just how many pi bonds and how many rings are in the molecule. Because if we have this formula, so C6H10, right, if we do the calculation, the DOU is going to be 2. Okay. Now, the DOU, right, so this is the number of rings plus the number of pi bonds in the molecule. So you could have 2 pi bonds, right, 2 double bonds. You could have a ring and a pi bond. You could have 2 rings, right? There's a ring here and there's a ring there. Okay? Or you can have the 2 pi bonds together to make a triple bond. Okay, if you had a carbon-nitrogen triple bond, again, that's going to be you're going to get a DOU of 2, stuff like that. And so books usually go into this really complicated sort of reasoning of all these rules you need to do with that. But usually what I say is just memorize the formula. And actually, I usually give you the formula on the test, and it's this formula here. It's 2 times the number of carbons in the molecule plus 2, plus the number of nitrogens, minus the total number of halides, or halogens. So this is fluorine, chlorine, bromine, and iodines. Okay, halides or halogens. Okay, minus the number of total number of hydrogens. All that divided by 2. Okay, now this plus 2 is a constant, so that has to be in there. So don't forget it. Okay? So on the test, I'll give you this formula. I won't give you the key, but I'll give you the formula. Okay? And so if we have this this formula here, right? So remember the DOU is 2 times the number of carbons plus 2 plus nitrogens minus halides minus hydrogens, all that divided by 2. Okay, and so if we're going to do this one, so the DOU, 2 times the number of carbons, so in this case it'd be 6, plus 2, that's the constant, plus the number of nitrogens, so in this case it's 1, minus the number of halides, right? So we have bromine, so that's 1, minus 10, all that divided by 2. Okay. So when we add it all up, right, so it's 12, 13, 14, 15. So 15 minus 11 by 2, right? So 4 divided by 2, 2. So that means, just like with the other one, right, we had 1 ring. We may have 1 ring, 1 double bond. We may have a triple bond. We may have 2 double bonds. Who knows? 2 rings. We don't know, but we know that it has something like, that something like that's going on. So if we're going to do, say this one, right? So DOU, let's do an orange, right? So DOU, 2 times the number of carbons, right? So 5 plus 2, right? Nitrogens, right? So 1 minus halides. We don't have any halides, so it's 0. Minus the number of hydrogens is 7, all divided by 2. Notice what we didn't use. We did not use the oxygen. That's not part of this equation, so don't put it in there. Oxygen, as it turns out, doesn't make presence of an oxygen. That doesn't matter. Okay, so don't put it in there. I did the slash in there to make sure you know that it's not the oxygens. Okay, so again, we're going to add this up. So 10, 12, 13. So 13 minus 7 over 2. So it's what? 6 over 2. So it's 3. So there we go. So these are example molecules of what it could be, right? So if it's 2, right, we could have a ring and a double bond. There's a whole bunch of different ways that you can do this. I just kind of made these up. This one here, right, you can have a ring and say two pi bonds, right? Carbon-oxygen pi bond and 2 carbon-oxygen pi bonds. That's fine. You could use either one. But again, it's this tells you, right? So this is going to be rings plus pi bonds, right? Okay. So just be aware. Okay. Thanks, everybody.